friends, I am Arwa and today's topic is quark. As we started studying about atom, we usually told the atom everything is made up of atoms. Atoms are the smallest particle. But as you dive inside the atom, you will find at the center of the atom you have nucleus, and around the nucleus you have electrons. And what is inside, and if you dive inside the nucleus, what you will get inside the nucleus you have two very special particles, that is proton and neutron. So proton and neutron, which is inside the nucleus, combinedly called as nucleons. This proton and neutron, which is inside the nucleus, now if you go inside this also, you will find these proton and neutron are made up of 3 quarks each. 3 quarks in proton and 3 quarks in neutron. Protons have 3 valence quarks, 2 up quark and 1 down quark. Up quark have a charge of +2 3 and down quark have a charge of -1/3, so that they add up to give +1, which is a charge of the proton. In the same way, neutron have 1 up quark and 2 down quark. When we usually told about that proton has 3 quarks, this is simply wrong, because the correct word is proton has 3 valence quark, which must be there at any given instant of time. But instead of these valence quarks, proton could have an additional up quark and anti-up quark pair, and both are just opposite to each other, and it can have other pair like strange or anti-strange charm and anti-charm quarks, and it can even have zillions and trillions of quarks and anti-quarks pair like this. This is quark and anti-quark pair, quark and anti-quark pair, so that it give a color quark and anti-quark pair, quark and anti. So it can have at any point of time it can have zillions and trillions of quarks and anti-quark pairs, which cancel out at any given instant of time and suddenly pop out and suddenly goes away, and there's a lots of crazy things going on over here. The quarks are held together by a strong force which is carried away by particles called, these are strong force in between these quark and anti-quark pairs, and these are gluons. Inside the heart of the proton, gluons and quarks just held together and wandered all around the speed. They just move all around with a speed of approximately equals to the speed of light. They collide and annihilate and destroy, and new pair pop up, and these crazy things going on over here. So this is our valence quark, and as we discussed earlier, at any given instant of time there are zillions and trillions of quark and anti-quark pair. So if this is our quark, then this is quark up quark, then this is our anti-down quark. If this is our up quark, then this is our anti-down quark. So at any given instant of time there may be a zillions and trillions of these quarks and anti-quarks pair. Now the conservation of properties of conservation of energy and conservation of other properties of these quarks and anti-up quarks pair must be conserved. So let's discuss about it. So at any given instant of time, if up quark and anti-down quark, up quark and anti-down quark pair suddenly pops out, and if it carries a charge of +2 3, let's say, then the opposite must have charge of -2 3, so that they will completely cancel out. If this has a spin of +1, then this must have a spin of -1, so that the spin completely cancel out, and we are left only with these valence quarks, which in addition gives you +1. Now you think, what about conservation of laws, because particles just appear and disappear out of nothing? The answer is no. Einstein's famous equation E is equals to mc square, which says a small mass can turn to lots of amount of energy and lots of amounts of energy can turn to small mass. Imagine this is whole proton, and quarks just contribute 1% of total mass of the proton. It's just as equal as saying, if let's say if this is a jar of 100 grams, and when you hold it or weight and suddenly weighs 1000 kg. Why? We know that if there's a lots of crazy things going on in this quantum world inside the proton, this is a quantum world inside the proton. So if there's a lots of crazy things going on, party of so many things, annihilate, destroy things, and suddenly pop up of new pair coming out, they must be using energy. They all are using energy, and there is also a gluon field. There is also a gluon field which holds them, which binds them. Okay, and all of these energy contributes to the mass of the proton. All of these energy mass contribute the mass of this mass to make up this proton. Now you may be wondered why. Because a particle gain mass when there is an impediment in its speed, and of course there is a lots of collision. There is a lots of collision and crazy things going on over here and there. Collision and crazy particles movement which hinders the speed and ultimately results into a mass which give mass to the proton. So this is the reason of quark and antiquark pair in and out, pops in and out. So they come at the cost of the energy. We generally get this type of picture from the net, that these three valence quarks which are held up by, which show in the figure mostly shows a spring around, a spring that holds these quarks together, and that spring represents the gluon field. But this picture is absolutely wrong now. As the study is going on, we now know that the strong force that hold together the quarks is actually when it suppresses these gluon fields, when it suppresses the gluon field and create a vacuum over here, and the energy to get rid out of this energy we require to get rid of these fluctuations, this gluon field, this suppression of gluon field, it requires a lots amount of energy, which it creates a flux tube that is nothing between them, it is a vacuum. So let's talk more about on this flux tube and how these quarks held together tightly, firmly. Let's talk about on this matter. Now imagine this is a beach having a lots of undulations or fluctuations in it. These fluctuations, the ripples are going and coming back in it. It's a like of this fluctuations of that going and coming around it, and these fluctuations represent the gluon field which binds the two quarks together. Okay, imagine these undulations or bumps coming and going. Now that is very important, because if you want to get rid of these fluctuations, it will take a lot amount of energy. So you are putting energy to remove these fluctuations. Now what will happen? And this is the key to bind these quarks or antiquark pair together. Important thing is, quark overall color of the quark must be white or colorless. If this is quark, then this is its antiquark pair. Both colorless has to be maintained in this. Okay, so if these fluctuations to get rid of these fluctuations, you are taking lot amount of energy. Presence of quarks subdue gluon fluctuations and create this flux tube. This is a flux tube between these quarks and antiquarks pair. This is quark and antiquark pair, and this is a flux tube between them. This is a region where there is nothing but a vacuum, and this is between quark and antiquark pair. This is just a flux tube. Nothing is there between them. This is just a vacuum. This is just a vacuum. All when quarks and antiquark pair form, fluctuate, we have in the gluon fields of these quarks and antiquark pairs subdue gluon fluctuation and create this flux tube, and that pair them to give a meson, that quark, and they pair them up and gives the mesons, quark. And what is meson? Meson is a quark and antiquark pair. So if you try to remove these fluctuations, if you try to subdue this, if these pairs when they form, if they subdue the gluon field, and if you put in lots of enough energy to just remove this fluctuation, then you really get a lot of big flux tube, right? So there is nothing. This is not like an elastic band. This is not like an energy that is pulling. There is nothing. This is just a vacuum. They just pull up by the force which attracts them up. That's it. There's nothing inside it. Now what happens if you put in lots of enough energy to just create a long flux tube, then you have put so much enough energy in it that you create another pair, you will not get just a long tube. Instead of this, if you put a lot of enough energy in it, so you are creating quarks never found alone. More you separate them, you are separating more and more. More you separate them, more energy you have put in to pull the quarks apart, and ultimately you have put enough energy in it to make you have put so much enough energy in it to make the mass of new quarks, which again combine with the original of the parent quark. Now you have created again quark and antiquark pair. Suppose this is red, then this is anti-red. If this is green, then opposite is magenta. So quark and antiquark pair. So these are our three valence quarks: red, green, and blue. Okay, now we know that on that we generally have a picture. Okay, these three quarks just attach with a spring which is called as gluon field, but that picture is totally wrong now, because these three quarks, they have nothing between them. They just have a flux tube. With the presence of these quarks subdue that fluctuation, subdue that gluon field. Due to that's a force which because that when you rid out of that fluctuations, that requires a lots of energy in it, and you have put in so much energy in it that force holds them. That vacuum, that flux tube holds them. That they created flux tube, and that force holds them. Okay, so what happens here? This is just a flux tube over here. So the quark pair just get rid of this. So you have put up enough energy in it. So this is a clear, though you are looking something over here, but there is really nothing over here. This is just a flux, this is just a vacuum in between them, and the proton, these quarks used to sit on these bumps on this flux, and when they pair up, they just get rid of this gluon field and this vacuum in it. There's nothing in it, and that force, this is the force, this force holds them together, which is a strong force. Okay, and as we know, red, green and blue, that combines to form a white. So quarks has to be colorless or either white. Might be you are thinking about restrictions of production of quarks and antiquark pair. Yes, one restriction is there. Total number of up quarks must be total number of that up these are up quarks. Total number of up quarks must be 2 more than anti-up quarks. These are anti-up quarks and these are up quarks. So they must be 2 more than anti-up quarks. And down quarks, these are down quarks and anti-down quarks. So down quarks, 1 more down quarks than anti-down quarks. Okay, so that they all cancel out with each other and we are left with our valence quarks. Okay, again, that it will create that flux tube and get rid out of these fluctuations. It actually requires, again I'm saying, it will require a lots of amount, and these quarks are sitting on these bumps and just clean all the fluctuations, and these actually holds these quarks together. This is strong force. Okay, so these are valence quarks. Hope you like the video. If you like my video, please don't forget to like, subscribe and share. It means lots to me. Thank you. And don't forget to comment also.